Right, so last class we started talking about the completely randomized block design. And the purpose of the completely randomized block design, or CRBD, is to allow us to compare 3 or more treatment or population means with when we are interested in grouping them based off of one treatment, but we want to control for the effect of another treatment at the same time, or for the effect of another variable at the same time. So effectively, what the CRBD is a one-way ANOVA where the information from this confounding variable, so the variable that we want to control for, is removed from the analysis of the variance. So you can see, for example, in the ANOVA table for the CRBD that's given on slide 12. In this ANOVA table, we have a treatment source, a block source, an error source, and a total. The block source represents that confounding variable. So this entry is meant to designate that we have taken information from the total variation and pulled it out of the error term. And the reason that it gets pulled out of the error term can be seen more directly when we compare the decompositions of the sum of squares for the one-way ANOVA and for the completely randomized block design. So we can notice that when we compare the one-way ANOVA and the completely randomized block design SST values, they are identical. So they have the same total sum of squares. When we compare the SSTR, so the sum of squares treatment, these are also identical because a completely randomized block design will always have the same number of observations for each of the treatments, which is little b. And then what happens is that the decomposition for the CRBD also adds an SSB term, where this SSB term is taking information from the SS error term of the one-way ANOVA. So basically what the CRBD does is it splits the sum of squares error of a one-way ANOVA into two components, the sum of square block and the sum of square error for the completely randomized block design. Now, the rationale for this is, again, if we know that this confounding variable is present in the experimental design, then we would want to control for its effect on the variable of interest, because it is, by description, it is a variable that will influence the outcome that we are studying. So it has a direct or a correlation with the response variable that we are measuring in the experiment. So there is a chance that if we do not account for it, it could mask or hide the effect of the treatment that we are actually interested in studying. Okay, so again, what the CRBD is essentially just a one-way ANOVA with one additional source, which is the block source. And the block source is meant to remove the information of the confounding variable from the the overall error term, or the within group sum of squares of the one-way ANOVA. Okay, now in accounting for this block variable, we actually end up with the ability to perform two tests. We have the usual test of treatment effect, which is what we studied in the one-way ANOVA case. And now we have a test of block effect, which is effectively just a test of a difference in the average value of the response variable across each block of our study. Right, so the general strategy for performing these tests, and even the way that you can think about the outcomes, is very similar. In the test of the treatment effect, you're just asking, is there evidence that the mean value at each level of the treatment are different? And with the block, you're asking the same thing, but instead in terms of the blocks. So is there evidence that the mean of each block, or rather, is there evidence that a difference exists between the means of each block? Now, this particular test, so the test of block difference in means, while its structure and its interpretation can be done in a pretty much analogous way to that of the treatment, it actually does provide us with a deeper meaning in that a rejection of the null hypothesis of a difference in block means would actually correspond to blocking being a useful practice. So essentially what we're saying there is if there is evidence of a difference between at least two block means, this implies that blocking was a useful practice because it allowed us to identify those differences. Whereas if we perform the block, if we block the experiment and we pulled the information out and there wasn't evidence of a difference, this could imply that the blocking strategy we utilized was ineffective because we did not properly structure the blocks to account for a difference in the means of the response variable. So typically when we perform the test about the block means, we're actually performing the test with interest in determining if blocking was a useful practice in the context of this experimental design. Okay, so to demonstrate these different tests, we are using a data set where we have 6 different treatments, which are fertilization timing schedules. We are measuring nitrate nitrogen content in the plants that were subjected to each of these treatments. So those values are given inside the table on slide 14. And we have created 4 different blocks. Now, this is the standard structure for a CRBD. So you can see that we have treatments or blocks lining either the rows or the columns of the table. And then we have means for each treatment block intersection, right? So for example, here, this value, which is this value 34.98, this would be designated Y11, and this is response at treatment 1, block 1, right? Whereas this value here, for example, this would be response at treatment 6, block 4, for example. Okay, so for each of the different treatment and block, or for the observations that are collected at each treatment in each block, we can compute a mean. So we have our block means lining the last column of the table here, and then we have our treatment means lining the bottom row of the table. And then we have an overall mean, which is 42.07. So this would be the grand mean. Now, from this raw data, we can compute all of the different sums of squares that would belong to the ANOVA table. The easiest ones to compute are, of course, SSB and SSTR. And I have an illustration of how SSB is computed below. SSTR would be done in the exact same way, except the leading coefficient would be a 4 rather than a 6. And we would just be taking the difference between each treatment mean and the grand mean squared and adding them together. If we wanted to compute SST, we would just take each value. So for example, 34.98, subtract the grand mean, square it, plus the next value inside the table, subtract the grand mean, square that all the way through. So for SST, we would actually have 24 different contributions to the calculation. Okay, so for example, SST would be the sum of 34.98 minus 42.07 squared plus 30.89 minus 42.07 squared plus all the way through to 43.29 minus 42.07 squared, right? And then you just add all of these together. Pretty painful, but that's how it would be done. And then to get the SSE, the easiest thing to do is just take the difference between the SS total and the SS block plus the SS treatment. Because using the formula for the SSE is a little bit more confusing because you have to consistently change the treatment and the block mean that you're working with. Okay, so The next thing that we looked at was an illustration of the test of a difference among the treatment mean, or a test of a treatment effect. So in this test, we are just running our standard ANOVA F test, but for the treatment effect directly. So from the ANOVA table, which is shown on slide 15, we can see that we have an F statistic of 5.59 and we have a p-value of 0.04 for the test of a treatment effect. The null and the alternative hypothesis are exactly like they were before. So we just have H naught alpha 1 equal to alpha 6, where alpha designates the treatment effect. And then we have the significance level on step 2, calculation of the test statistic on step 3, which would be done through an ANOVA table construction. You don't have to use the ANOVA table, but it's a nice way of summarizing the information. You can see that in this illustration, I've also given the p-value. So based off the p-value, we can reject H naught since it's less than alpha. And then we can conclude that there is evidence of a difference among the 6 different treatments that we are studying, or sorry, there is evidence of a difference among the 6 treatment means that we're studying in this experiment. Okay. Now, the next exercise was the test of block effect. So we started working through this last class. So this exercise is basically just using the block source from the ANOVA table, and we're operating in the exact same way that we would for the treatment effect. So here we have beta 1 equal beta 2 equals to beta 3 equals to beta 4. So the block effect is, or there is no block effect, or that the block means are equivalent, versus the alternative that not all block means are equivalent. Okay. On step 2, we state our significance level, and then on step 3, we compute the test statistic. Again, the test statistic would just be found in the normal way. So you can see here we have MSE and we have MSB and MS error. So this F statistic here, as shown on the other slide, would just be 65.67 divided by 7.20, which is equal to 9.123 repeating, I believe. 12083. Okay. All right, so now we just have to make our decision about the null. So we have to determine if this gives us evidence for or against the alternative hypothesis, or for or against the null hypothesis. Okay, so if we take the p-value approach, this will be done just like it was in a one-way ANOVA. So we sketch out our F curve. All right, we mark down where our test statistic falls. All right. And we are looking for the area to the right of that test statistic. Okay, so our DF here will be the degree of freedom for the block, which is 3, and it'll be the DF for the error, which was 15. All right. So we are looking for a p-value using the F table, and we need 3 and 15 degrees of freedom. All right, so we're going to open up our F table here. We're looking for 3 and 15. Oh, first try. So that's going to be on page 3. Okay, so here's 3. Here's 15. Here are the values that we're going to be working with, and we're utilizing this column here. Okay, so we can see that our test statistic is larger than the largest listed value. All right. So therefore, the area to the right of the test statistic is going to be smaller than the smallest listed value, which is 0.005. Okay, so in this case, we can say since the probability that F exceeds 9.1208 is less than 0.005, then the p-value is less than 0.005. right? And that's obviously going to give us the ability to reject H naught. Okay, so if we take the critical value approach, we should be able to show the same thing. So we start by sketching out our F curve. Right. Okay, so in this case, we're going to be looking for an F value on 3, 15, and 0.05. Okay, so the size here is size 0.05. Right, so if we go to our F table, we're going to match 3, 15, 0.05, and that gives us 3.29. Right, so the critical value for this test is 3.29. Right, and then we can see that the test statistic is inside the rejection region. Right, so we can reject H naught in this case. Okay, and then on step 6, we'll just have sort of the standard conclusion here. So we can say at the 5% significance level, the data provide sufficient evidence to suggest there is a block effect. Okay, so I have at the 5% significance level, the data provides sufficient evidence to suggest that there is a block effect. All right. So hopefully you can see that the process of hypothesis testing that comes out of this CRBD approach is very similar to what we had before. So from a technical standpoint, questions that are asking you to perform CRBDs and calculate test statistics and determine if there's an effect among the treatment means, these are very repetitive, and I would say the expectation is that you'll be comfortable with these because you've seen them so much in the last few weeks. The really interesting parts are the questions that relate to why we are actually doing this. So the questions that are asking about what blocking is, what the confounding variable is, how the block design removes information from the error term, the effect that this has on the test statistic. So these are the things that we really want to think about and try and internalize, because the process of conducting the test is starting, well, hopefully you can see is becoming very consistent and should be familiar as we progress through each of the levels or the different types of ANOVAs. So you can expect, for example, on assignment 4, some of the early questions to be things like, what is a confounding variable? Give an example of a confounding variable. What does what does like how is the information in a, or how does the decomposition of the sum of square for a CRBD account for the block effect? what happens or what would be the expected result if a confounding variable is present, but we didn't account for it? So what would this mean in terms of, say, the result of the ANOVA procedure that we are running? Okay, so thinking about comparing the one-way ANOVA procedure to the CRBD, and again, that overall influence of the blocking source and what that would do to the error term and what that could do to the test statistic and conclusion of the test. All right. Okay, so the next, well, any questions so far? Okay, so the last part of this lecture set is really just a discussion on how we would conduct a multiple comparison after we have performed a CRBD. And as you will see, the process for conducting a multiple comparison when we're using a completely randomized block design is identical to the process that we had discussed for the one-way ANOVA. The only difference is that we typically don't compute multiple comparisons for the block means. So we only focus on a multiple comparison of the treatment means because, again, in a CRBD, we are still only interested in comparing the results of, or in comparing the means from the explanatory variable that is of interest to us. So if we have evidence that there's a difference among the treatment means that we are studying, then we would be interested in performing a multiple comparison. So the same way that a one-way ANOVA would essentially be the first check before we go through and compare the means individually, the CRBD would be the first check before we go through and compare the treatment means or compare all before we perform all pairwise comparisons of the treatment means. Okay, so the starting spot for the multiple comparisons in a CRBD is the same as the multiple comparison for the one-way ANOVA. So we begin by defining the general contrast of the treatment means. Now, as a reminder, because this question has come up a few times through email, a contrast is a linear combination of the means. But the contrast requires that the coefficients of that combination add to 0. So you can have a linear combination of the means, which means that the means are added or subtracted to one another, no multiplication or division, and no other type of transformation. But the coefficients don't have to add to 0. And if that is the case, then you have a linear combination, but you don't have a contrast. Okay, so for example, okay, so this would be an example of a valid contrast. Sorry. Okay, so this is a valid contrast because you have C1 equals -1, C2 equals C3 equals a half. Therefore, -1 plus 1/2 plus 1/2 equals 0. The linear combination could be gamma equals -μ1 minus 1/2 μ2 plus 1/2 μ3. Okay, so here you'd have C1 is -1, C2 is -2, a half, C3 is a half. Okay, so therefore -1 minus 1/2 plus 1/2 equals -1. So these are both linear combinations, but the first one is a contrast because the coefficients add to 0. The second one is not a contrast because the coefficients add to -1. And then the situation where you would have neither would be something like gamma equals negative mu1 times mu2 plus mu3. Okay. So in this situation, the coefficients would be negative. So you'd have C1 equals -1, C2 equals 1, C3 equals 1, right? So therefore, -1 plus 1 plus 1 equals 1. Okay, so this is not a contrast because it's not a linear combination, and it's not a linear combination because you're multiplying the means together. Yeah. Right. And then this is related to question 7 on the assignment. So does that make sense? Does anyone have any follow-up questions? Charlie, I can ignore this question? Is that?
Yes, that's all good. Thank you.
Yeah. Yeah, I think the both is a typo. It can't be both. So, like, because both would just be the contrast. Like, it's because the linear combination is a subset of the contrast. So it wouldn't make sense for it to be both. So it should just be like linear combination, contrast, or neither. I'm just going to look at it here. Yeah, it shouldn't be both. I'll just take that off and I'll repost it. Okay, I'll do that after. Yeah, sorry for the confusion on that one. All right, so again, the main reason that we're setting up the contrast here is just so that we can compare the treatment effect or the means of each level of the treatment. So the goal is exactly the same as it was in one-way ANOVA, and the process is going to be exactly the same. We start by defining a general contrast of the treatment means, which is what we have on slide 18, same definition as before. And then we can show, okay, this sampling distribution of the contrast is exactly the same as it was from the one-way ANOVA. The only difference, and it's a very subtle difference, the degree of freedom for the test statistic is going to be the DFE from the CRBD because we are following a CRBD. So the degree of freedom that we attach to the T value will be the DFE from the CRBD. But everything else is exactly the same. And actually, running a multiple comparison out of a CRBD is a little bit easier than running a multiple comparison out of a one-way ANOVA because you are guaranteed to have the exact same sample size. So you can see here, we have subscript B in the formula for the standard error. That's because every treatment can only have B entries, 1 per block, right? So you only have to compute the margin of error once when you're running a multiple comparison out of a CRBD. So in that sense, it's actually easier from a having to run the computation by hand point of view. Okay. Any questions? All right. Okay, so the actual process for performing the multiple comparisons will progress exactly like it did in the case of the one-way ANOVA. We start by fixing our overall or the experiment-wise error rate. Most often, we just use the exact same alpha that we use for the ANOVA. So in the examples that we started with today, alpha was equal to 0.05. Then what we do is we essentially penalize that alpha value to find the individual comparison alpha. So alpha star or alpha subscript I. And that's just going to be alpha divided by 2m. Okay, so alpha I equals alpha E divided by 2m. Okay, so that's the same thing as alpha star over alpha. And then essentially all we do is we find the differences in the treatment means. We compute the margin of error. Again, we only have to compute one margin of error because the sample size is the same for every single combination. And then we just determine which differences are larger than the margin of error. And again, if which absolute differences are bigger than the margin of errors, because if the absolute difference exceeds the margin of error, then the interval is not going to cross zero, so you have evidence of a difference. Right? So it's the same process that we saw for the one-way ANOVA. The only differences are that the degrees of freedom is going to be the degree of freedom from the CRBD. The MSE will be the MSE from the CRBD, but you still wouldn't really be able to mess that up because you're just working with the error source. And then we only have to compute the margin of error once because we have a consistent number of observations for every treatment. Okay, so let's say for the example that we started with today, we want to perform the multiple comparisons. Okay, so we set the experiment-wise error rate to be 0.05. Now we have to compute M. Okay, so M is going to be equal to the number of treatment means, choose 2. So we have 6 choose 2, which is equal to, what's 6 choose 2? I don't know off the top of my head, actually. 1, 6, 5, 10, 15. I'm going to say 15. Pascal's triangle. I feel good about this answer. Okay, and then we're going to compute alpha star. This is the same thing as alpha I, just so that we're on the same page. Okay, so this is going to be alpha E divided by 2m. So this is going to be 0.05 divided by 2 times 15. Okay, so that's going to be 0.0016 repeating. Okay, then we're asked to rank the treatment means. Like we can do this, but it doesn't really matter, but it just makes organization and like finding the differences a little bit better. So just for completion's sake, we can sort them. All right, and now we have to compute the margin of error. So the margin of error is going to be the same for every single comparison because again, we have the exact same sample size for every single treatment. So here we're going to have a t-value on alpha I, comma, DFE multiplied by the MSE over 1, multiplied by 1 over B plus 1 over B. Okay, now, since t-table doesn't give t subscript 0.0016, use t 0.005. Okay, so a limitation of our t-table is that the lowest right tail area that we can actually achieve is subscript 0.005. So for this particular experiment, we're forced to only use t subscript 0.005. So if we go to our t-table, sorry, one sec. So if we go to our t-table, we are going to use T subscript 0.005. We have 15 degrees of freedom from our CRBD. So that gives us 2.947 for this particular exercise. Okay. So this is going to be T on 0.005, 15 multiplied by 7.20, 1 over 4 plus 1 over 4. So that's 2.947 multiplied by the square root 7.20. And that's going to be a half. And that gives us a margin of error of 5.591. And all we have left to do here now is just compute the absolute differences between all of the treatment means and then check to see which ones are smaller than the margin of error or which ones are larger than the margin of error. All right, so I'll just give it a second in case anyone's writing it down. Okay, so in table 6 here, I have the absolute differences between the treatment means and the experiment, right? So the first value here, that's the difference between mean 1 and mean 5. The second value here, this is the difference between mean 1 and mean 4. Okay, so our margin of error was 5.591. So we are looking for any margin of error that is larger than 5.591. Okay, so we will star those. So here's one. All right, here's another one. Here's another one. And here's another one. Okay, so there are 4 combinations or 4 pairs of means that are significantly different from another at the 5% significance level. So we've shown that, or we can show that treatment 1 or mu 1, or sorry, alpha 1 versus alpha 2 is significantly different. Alpha 1 versus alpha 3 is significantly different. Alpha 5 versus alpha 3 is significantly different. And alpha 4 versus alpha 3 is significantly different because the absolute difference is larger than alpha. Okay, so since absolute alpha I minus alpha j is greater than E, we have evidence of a difference. Okay. Right. So this diagram below, this line diagram, this is just an alternative to representing the outcomes. So the way that this works is any pair of treatment means that are connected by the dashed lines would represent no difference. So the idea is that these dashed lines represent like equality. Okay, so this diagram shows means that are not different, right? So this is saying that mean 1 and mean 5 are the same. Mean 1 and mean 4 are the same. Mean 1 and mean 6, statistically speaking, are the same. Right, so in general, I don't really recommend this type of diagram for visualizing the results because I think it's a little confusing because we're typically searching for differences, not for equality. So this diagram shows equality, not difference. But the so what you would then have to do is work through the diagram and go, okay, what isn't listed here? And then you would give your conclusion in terms of what is not listed. So it's much easier to just look for the pairs of means that are statistically different from one another and then just report on those. So here we can say at the 5% significance level, the data provide sufficient evidence to suggest a difference in mean nitrate nitrogen content exists between treatments 1 and 2, 1 and 3, 5 and 3, and 4 and 3. Right? And that's done simply by comparing the margin of error to the absolute differences. So in any situation where the absolute difference is larger than the margin of error, that gives us evidence of a difference. In all other cases, that interval would cross 0, so there would be no evidence of a difference. And this diagram reflects the places where we have no evidence of a difference. All right, good stuff. Okay, so yes, please.
Sorry, I think it's just maybe because I can't see the other slide, but where are the numbers from this table coming from?
Oh, yeah, so it's they're the absolute like differences in the means. So for example, okay, so I actually need to pull out. All right, so if we go back to slide 14, it's the differences between each pair of means that are shown here. Okay, so for example, sorry. So these are from slide 14. Okay, so for example, the first difference is mean 5 versus mean 1. So if we go to slide 14 and we take mean 5, which is 39.51, and we subtract 38.28, then we are going to get the 1.23. Okay, so this here is, for example, 39.51, 38.28.
Okay, that makes sense. And then how come the numbers on the top and the side are not in order in any way?
It's because I'm following the ranking from the previous slide. So on
Okay.
here we rank them from smallest to largest. So this I think was 1, 2, and then these would be whatever they are from the table. And so we're just following that order. So it'd be 1, 5, 4, 6, 2, 3.
Okay. Okay, yeah. That makes sense.
Cool. Thank you. Yeah, and then actually here, this is actually an easier way to see it because now you have 5 minus 1, then you have 4 minus 1, 6 minus 1, 2 minus 1, 3 minus 1, and that's what's given in the first row here. Any other questions? Right. Well, that actually brings us to the end of the CRBD study, anyways. So that's the end of lecture set 6. So on Friday we'll start lecture set 7, which is on two-way ANOVA. So this is the two-way ANOVA is an extension of one-way ANOVA where you have 2 explanatory variables that are of interest now. So we had one-way ANOVA where you have 1 response, 1 explanatory variable. You have CRBD where you have one response, 1 explanatory variable, and a confounding variable. And next we're going to see two-way ANOVA where you have 1 response, and then you have explanatory variable A and explanatory variable B. So you want to test both of them. Okay. In terms of the course outline, we're slightly behind schedule because we're supposed to finish two-way NOVA by the end of this week, but we won't finish lecture set 7 in one class. So we're not terribly behind, but I'd say we're maybe a lecture to a lecture and a half back of what was estimated in the course outline. Yeah, so on Friday, we'll start lecture set 7. Assignment 3, I believe, is due Friday, and then it's reading week next week. And there's still about 5 minutes left. So if anyone has any other questions about the assignment or whatnot, I'm happy to hang around and answer those. Otherwise, I will talk to you guys on Friday afternoon.